Okay, impulse is the topic of today's video, and impulse is related to momentum. And we learned last time that momentum, P, it was a vector, so I put a little arrow up there to designate that. And we said that was equal to the mass times the velocity of some particular object. So you could calculate the momentum of any given object simply by knowing its mass and its velocity. And we recall that velocity was a vector, so it was essentially, it had a magnitude, so many meters per second, and a given direction. So momentum has a direction, and it has units of kilograms times meters per second. That's the units for momentum. Now I'm going to derive for you what impulse is all about. Impulse, let me just state it up here, is defined as the change in momentum. So impulse is this change in momentum. And a change in momentum, you remember we used to use those Greek letters to designate things, and the Greek letter for change was always delta. So the change in momentum would be delta P, or we can rewrite that as delta mv, because mass times velocity is momentum. So this change in momentum here is the same quantity over here, mass times velocity. It's the change in linear momentum. That's what impulse is. It's the change in momentum. Let's try and understand this now. Let's come over here, and we want to go back to Newton's laws. Remember Newton's second law of motion. Newton's second law of motion says that a net force is equal to the mass times the acceleration. So F equals ma was Newton's second law of motion. And acceleration now, let me just put a little bar out here. Acceleration was, if you recall from a couple of chapters ago, simply the change in velocity over the change in time. In other words, if you had an object that was going at some particular speed and you looked at it a couple of minutes later and it was going faster or slower, then we said that there had to be acceleration over that time interval that you were interested in. So delta t is the time interval that you're interested in changing the velocity. If the velocity changes, you've got an acceleration. So let's rewrite this Newton's equation, substituting for a over here, this expression for change in velocity over change in time, because that's what acceleration is. If we do that, we will see that the net force is the mass times the acceleration, which happens to be change in velocity over change in time. Okay? So far, so good. Now, if we take this equation, all right, and we multiply both sides of this equation by time, or by the change in time, we get this. We get force times change in time is equal to mass times change in velocity. This change in velocity, let's rewrite. Remember, change in velocity was some final velocity minus some initial velocity. Anytime you have a change in something, it's always final minus initial. If it's change in position, it's the final position minus the initial position. If it's a change in velocity, it's the final velocity minus the initial velocity. If it's the change in acceleration, all right, it's the final acceleration minus the initial acceleration. Change, delta, always means final minus initial. And now if we look at this side, mass times v final is mv final. Mass times v initial, mv initial. This is just your final momentum, because momentum we defined as mass times velocity. So this is just your final momentum minus your initial momentum. And this guy over here is simply the change in momentum P, which we talked about up here. So we see then that force times time gives rise to a change in momentum. Now, I could just as well take this mass here. You see this delta V? I could put this delta out here. Since mass is a constant, we could put that delta here, make this delta mv, because it's really a change in mv, as you see over here, which is a change in momentum. This quantity here is what we call impulse, and this is our change in momentum. All right, so impulse is a change in momentum. It is force times time. So you might say, well, yeah, that's really nice, but what does this mean, force times time? Here's what it means. Let's go over here. So I'm running out of room. Or maybe, and let's just use a different color here. Let's say if I got something going in space, so there's no air resistance, and it's happily traveling by Newton's first law of inertia. An object in motion wants to stay in motion at a constant velocity. So let's give this guy a velocity here of 2 meters per second. And it'll stay that. It has a mass. I don't know what the mass is. Let's just put a little m in there. It stays at that velocity by Newton's law of inertia. Until what? Until some force comes along. Now, in order to get this guy to go faster, the only way to make this velocity change is to apply a force. Something's going to have to come up from behind it and give it a kick to make it go faster. So there's our force, which comes up behind the object and pushes it to make it go faster. If it pushes it, what we're going to say is, well, the force, something has to contact our little round yellow object over here. Something has to make contact, physical contact with it, and apply a force for a certain amount of time. Unless, of course, you're talking about some kind of non-contact force. But in any event, you're still going to have this guy here experience some kind of a push for some length of time. So a force is applied for some time t, or delta t, some time interval. And if you apply a force, you give it a push, you wouldn't be surprised if I told you that what happens is our same little mass over here is now going faster. So let's make it go faster. And the reason it went faster is because I applied some force. Something pushed it. For some interval of time, something pushed it, something made contact with it, some force acted on it for a certain time, and it made it go faster, because that's what a force will do. If you're going at a certain speed, the only way to speed up or to slow down is for some force, external net force, to act on it. That's Newton's law of inertia. Well, look what happens in that case. You apply a force F for a certain time interval, and the result is that you speed up. Well, if the object speeds up, its momentum had to change, because momentum is mass times velocity. So the momentum here, which we'll call the initial momentum, will be the mass times the initial velocity here, times v initial, which we'll call 2 meters per second. The momentum here, which we'll call the final momentum, is simply the mass. Whatever the mass is, we didn't say what it was for this problem, but whatever that mass was in kilograms, times this final velocity here, which would be 7 meters per second. So we have an initial momentum here. Some force comes along, pushes it for a certain time, certain number of seconds, say, which results in the momentum increasing in this case, with the momentum changed. And we will see that the equation is this force here is F, that's acting on the object, times the time interval that it acts, will be equal to the change in momentum. In other words, this force times the time is going to be equal to the final momentum minus the initial momentum. And this is what we call, once again, impulse. Impulse changes the momentum, so it involves a force, always. Let's see what else we want to talk about as far as impulse is concerned, so maybe we understand it a little bit better. Suppose I have suppose I have a football, and someone's going to throw the football. So let's say someone's hand is on the football here. Some guy's getting ready to toss this football. This is our guy here, right? He's going to throw the football, and the football is going to move out in that direction. So the fact that his hand is on the football, whipping this football overhead, so the football is going to move with the guy's hand in this direction, and he's finally going to release it here. Here's where his hand will release the ball, and the ball goes flying off in that direction with some velocity, right? So let's give it some v in that direction, and the football, of course, has some mass m. Now, if we look at it here, right here, the initial velocity of the football is 0 because it's still and it's not moving, it's at rest. He's got his arm back, it's getting ready to be thrown. The ball isn't moving, it's got initial velocity of 0. So its momentum, which is its mass times its initial velocity, this initial momentum, has to be 0 because it's not moving. In order to get it moving, he has to apply a force. That comes from his fingers and the palm of his hand. He's going to apply a force on the football for a given time, delta t. Delta t is how long it takes to go from this position here to this final position here where he lets go of it. At this point here, once the ball is let go, it no longer feels or experiences the force at all. It's going on its own, so the force only acts on the football as long as his hand is in contact with it. So as long as this guy's got his hand on the football and he's moving his arm, he's giving force to the football's gaining kinetic energy now. Remember, 1/2 mv squared? But more important for our discussion today, the football is gaining momentum. It starts with 0 momentum because its velocity is 0. And up here, it's got a new momentum, a final momentum when it leaves the guy's hand, equal to the mass times some final velocity, which we'll call v final up here. So you can see that the momentum of the ball changed from 0 to some final value because he gave it velocity, and that happened because the force of his hand was in contact with the ball for a certain time duration, and that produced the change in momentum. So we can see here that this force times the time is the force of the guy's hand times the time that he was in contact produced this change in momentum, which in this case was mv final minus m0 because it was at rest. So this is our change in momentum going from rest to some final velocity. All right, we'll just cover impulse a little bit more in the next video, and I'll give you 1 or 2 more examples.